Hello friends, this video on aldehyde ketones and carboxylic acid part 14 is brought to you by examfear.com. No more fear from exam. Now we'll talk about the nucleophilic addition reaction. Just word strong actually. We'll talk about the mechanism. So there are two options. One is the nucleophile which is going to attack this carbonyl part is either strong or weak. So let's take one scenario where this guy is strong. The nucleophile is strong with a negative charge, let's suppose. Correct? So if this nucleophile is strong, the negative charge, it's a strong nucleophile. So what will happen is, this we have seen this so many times back. If you see the reaction mechanism, we have discussed this. This carbon has, oxygen is more electronegative than carbon. Oxygen will get slightly negative charge, carbon slightly positive charge. Since carbon is slightly positive charge, this nucleophile with a negative charge will attack this carbon, and this bond will break in this fashion. So with this, if you see, oxygen gets negative charge and the nucleophile is attached here, right? And then a hydrogen H plus will come, and this O minus will attack this H plus. This is how it will happen given the nucleophile is strong. In the next case, the nucleophile is weak. So in this case, what will happen is, first my H plus will come, right? So now this, what will happen is, this H plus, this guy will attack this H plus, and this bond will again break in this fashion. So what happens is, this becomes OH and carbon gets a positive charge. This is my carbon, get a positive charge. And then my nucleophile, my weak nucleophile actually will easily come and sit here. So there are two possibilities. One is, the nucleophile is strong, the nucleophile does the attack first. But if nucleophile is weak, then some H plus comes and then it attacks this O minus, creates carbocation, and then nucleophile can easily come and attack that carbocation. Correct? So this nucleophilic addition reaction can happen by two ways. One is, the nucleophile is strong, the other is the nucleophile is weak. Life is a race, and as I told, aldehydes and ketones, they have similar reactivity, right? So there has to be a case where, or we have to tell whether aldehydes is more reactive or ketone is more reactive. Which one is more powerful, whether aldehyde comes first or the ketone comes first, right? So there has to be a decision done. So let's understand which one is more reactive. Is it aldehydes or is it ketone? So if we observe that aldehydes are more reactive, so this guy is aldehyde is more reactive and this guy is ketone. This is observed that aldehyde comes first. They are more reactive than ketones in nucleophilic addition reaction. As far as the nucleophilic addition reaction is concerned, aldehydes are more reactive. And there are two reasons. The first is steric hindrance and the second is the plus I effect. I'll tell you both. So this is my aldehyde and this is my ketone. So if you see, this is my carbon which has to be attacked. The first reason I told you steric hindrance, because if you see here in this case, for a nucleophile to attack, I have a nucleophile here. So there is no less space to attack because of steric hindrance, right? But nucleophile can attack this guy because there's more space to attack. Because since there's a hydrogen here, right? Hydrogen is small and it provides comfortable space for nucleophile to attack. So going by that parameter, if you see, aldehyde is more reactive because aldehyde can be attacked easily because of the steric hindrance. The next is the plus I effect. As I told, oxygen is more electronegative than carbon and oxygen develops partial negative charge and carbon develops partial positive charge. Partial negative charge, partial positive charge. Now this partial positive charge, if you see, and these are my alkyl group, they have plus effect. This is neutralized by these alkyl group. These provides electron to this carbon. So this positive charge is not that great, right? But this positive charge is great because this has two alkyl group attached to it to minimize the impact, but this has only one alkyl group. Hydrogen doesn't provide electrons. So in that case, it has more positive charge on this carbon. Correct? This is my nucleophilic carbon. This is my nucleophilic center actually, because it has more positive charge, and higher is the positive charge in this carbon, the greater is the chance for nucleophile to attack. Correct? This carbon has less positive charge. Why? Because whatever positive charge it had, it got nullified, or it is diminished a little bit by the plus I effect of these two alkyl groups. So there are two reasons why aldehydes are more reactive. One is aldehydes, since it has one part as hydrogen, it is RCOH here, and here it is RCOR dash. Both are bulky, right? So here you have H, here you have R dash. So if you see, this has more space, this has less space. So due to steric hindrance, nucleophile can easily approach aldehydes, but they can't approach ketone. That is one thing. And because of plus I effect, since there are two R group attached, they minimize the plus charge on carbon. Here only one R group attached. They do minimize, but to a lesser extent. So this carbon in aldehyde is more positive. It has more positive charge. It has less positive charge. Since it has more positive charge, nucleophile can easily attack. Hope you understand why aldehyde is more reactive than ketones for a nucleophilic addition reaction. Please note, I'm talking only about this nucleophilic addition reaction. This race is all about nucleophilic addition reaction only. Let's take one numerical here. Let's find out which one is more reactive towards, again, nucleophilic addition reaction, benzaldehydes or propanol. Both are aldehyde now. So as I told, there are two parameters. One is the steric hindrance, which we have learned till now, and there is plus I effect. So let's see, steric hindrance, this is a big benzene ring, so steric hindrance is more, right? And this is steric hindrance is less. Steric hindrance is more here. So going by steric hindrance, which one is more reactive? Which one is less reactive? So I think benzaldehyde is less reactive, right? By steric hindrance, because it has more steric hindrance. Difficult for nucleophile to attack because of the big size of benzene here. But here it can attack. So because of steric hindrance, benzaldehyde is less reactive. Correct? Let's the next parameter. The next parameter we have is the plus I effect. So this is my carbon and this is my carbon I'm talking about. So I have put this here in green. Now this benzene ring is electron withdrawing, and this has slightly positive charge. We have seen slightly negative. So benzene ring has electron withdrawing capability, and this alkyl group has electron releasing capability. So with I effect, we can see that since a benzene ring sucks electron or withdraws electron, this carbon is all the more positive. So with this, propanol is less reactive. Correct? Because if you compare by the I effect, right, the propanol actually will be less reactive because this alkyl group is giving electron and is becoming less positive, and this benzene ring is taking electrons from this carbon and becoming all the more positive. This carbon is more positive than this carbon, right? Now we are confused. The first thing says benzaldehyde is less reactive, second says propanol is less reactive. So here we have to see the third parameter also there is resonance, because the moment we talk about benzene ring, we talk about resonance. So let's see what happens if a nucleophile attacks this benzene. If a nucleophile attacks this benzene, I have a benzene, benzaldehyde actually, and let's suppose a nucleophile attack, this becomes minus charge, and this is a nucleophile here. So what happens if a nucleophile attacks this? Then you get this compound actually, O minus H and nucleophile. This is what you get. Correct. Now check if is this stabilized, is this stable due to resonance? Can we check that? So we will not be able to draw a resonating structure here. Structure of product expected, right? Because if you see, if you want to form a bond, you have to break something. So resonating structure is not possible for the product. Let's see for the reactant, if the resonating structure is possible or not. So the reactant is this guy, COOH. This is my reactant, correct? So let's see if a resonating structure is possible. It becomes negative, it becomes positive, right? And let's break this bond. With this, what you get is, let me see, CO minus H double bond here, and here you get a positive charge here. Let's draw more structure here. This bond breaks. Correct. Now we'll break this bond. This is exactly same I'll draw. This is a negative charge all over the place. Sorry, I missed that. Yeah. This bond breaks, so you get here, and you get a positive charge here. And again, it goes back. So if you see, this is my reactant. Now I see the reactant has more resonating structure, and the product is not having the resonating structure. So if I talk from reactant to product, for this case, my reactant is stable and the product is not stable. Correct? Because product we don't have many resonating structure, but for reactant we have so many resonating structure. That means it is stable. That means it is less reactive. So with this, we confirm that benzaldehyde is less reactive. Hope you understood what I'm trying to say. See, we were confused. Steric hindrance says benzaldehyde is more reactive. Plus side effects says benzaldehyde is more reactive. Correct. Now then we saw the resonance. We saw that for the product, we are not able to draw any resonating structure. We assumed that the reaction happened in nucleophile attack. But for reactant, we were able to draw resonating structure. We concluded that the reactant is more stable than product. So if reactant is more stable than product, that means there's a high chance that the reaction won't happen. Correct? The reaction is more stable. So that means the reactant is less stable, less reactive. And that's what the reactant here is, my benzaldehyde. Because we are talking about the resonance only for benzaldehyde. We are talking about the resonance. We are not talking about the resonance for propanol. So with this, we conclude that benzaldehyde is less reactive. Thank you. Visit our website examfear.com to watch more and more quality educational videos. You can also attempt free online tests that are there in our website. You can also get access to tons of free study materials, and you can also find free tutors and mentors in this website. Thanks a lot for watching.